Hello, dear students. First of all, apology for a long gap. So I was actually shifting one place to another place. So that's why most of the July I got very busy with this. But okay, let's have a fresh start and hope if everything gets fine, then we'll be continuing very regularly in July, August, and September. So let's start. Let's begin today. In this class, we'll study error analysis. This is the third class. So if you haven't watched the second and first class, so please do that. After this class, you'll again get an assignment of error analysis. So, okay, let's begin. Before we begin error analysis, just have a quick look. So I make myself a little bit smaller there. So this course link is this. If you are watching, if you're not subscribed it yet, if you're watching this class first time, so please go to this link. This link will be given in the description, video description also. The course fee, as this course is running first time, so the course fee is just rupees 999, not the regular price of 2000. Okay. So the last two classes, we learned about dimensional analysis and vectors and differentiation and integrations, all the very basic mathematics part was there. In this class, we'll learning about error analysis. So as we told, everything there. So let's begin. First, have a brief outline of what we'll be discussing here. We'll be discussing how to write the data, how to represent the error, statistical analysis of small data set, statistical analysis of large data set, propagation of error, this will be the most important part, and finally error in counts. We may have this are bold. Okay, that's great. So this is a brief outline of our discussion. Now first start with how to write the data. Suppose you are asked to find time period of a pendulum. You know what time period of a pendulum is. Time period of a pendulum is t. T is 2 pi square root of over L by G. It will, is it okay or previous was okay? I think previous form was better. So this is 2 pi square root of L by G. Suppose you are given that L is 0.24 meter and G is 9.81 meter per second square. That means I am telling you that, okay, my friend, you have a danda, you have a pendulum. This is a massless. So, okay, you have a pendulum with length L equals to 0.24 meter. Let's find the, what will be the time period? That's the important question. How you represent the time period? If you just put the value of pi, multiply it by 2, then make a square root of that L by G. L is 0.24 and G is 9.81. That exact calculation will give you an exact wrong answer. The calculator will give this. This is the calculator will give this. But that will be wrong. Right answer you should report the time period is as 0.98 second. Not all the other part. You shouldn't write these digits. Why is it so? See, I am not telling you any uncertainties over this, that L is 0.24. That doesn't mean anything. Or it means something which is not inherent, not explicitly written. If I tell you that L is 0.24 meter, that means L is 0.24 with the uncertainty of plus minus 0.1. Otherwise, I would have written as 0.2400. That means 0.24 meter and 0.240 meter, 0.2400 meter are not same. They are not same. That means your confidence is up to this 2-digit. This means your confidence is up to this 3-digit. This means your confidence is up to this 4-digit. That's interesting. If I tell you that my distance from, say, my home to your home is 133 kilometer, that means that we are dealing with 1 kilometer of error. 133 kilometer. If I am sure up to 1 meter, then I tell you the value of meters also. And if the distance is exact 133 kilometer within a confidence of 1 meter, I would write 133.000 meter, sorry, kilometer. So we'll discuss this later also. So are you watching me? Very small. So I can be a little bit bigger. No issues. So the concept here is, when no uncertainties are given, report your value with the same number of significant figures as the values of your source variable. That means here we have two significant digits, 0.24, and G is 9.81. So we don't have much confidence beyond these 2 digits. That means we are measuring the length in confidence up to centimeter level. 100 centimeter is 1 meter, up to centimeter level, not millimeter level. So when no uncertainties are given, report your value with the same number of significant figures as the values of your source variable. We have 2 digits of significance after decimal, 2 digits of significance after decimal. So using this two, how can you get a measurement which is correct up to, say, 6 digits after decimal? You cannot have that. You cannot have that. If it is 2.433578 or something was reported, then your length wasn't very accurate, and G is given up to 4-digit or 6-digit accuracy, then you would have reported by it 6-digit accuracy, the time period. Here we have 2-digit accuracy, 2-digit accuracy. T will be up to 2 digits of accuracy. That's why we ignore this part and I report this. Okay, I think you got it. We had a very exact same problem which appeared in CSI NET exam in June 2019. Just watch over it. It tells you, in an experiment to measure the acceleration due to gravity using a simple pendulum, the length and time period of the pendulum are measured to 3 significant figures. The length and time period of the pendulum are measured to 3 significant figures. The mean value of G and the uncertainty delta G of the measurement are then estimated using a calculator from a large number of measurements and found to be 9.82147 and 0.0235. Which of the following is more accurate way of presenting experimentally determined value of G? Same question, is it? We have T is 2 pi L by G. Hence you can say G is 4 pi square L by T square. So you are measuring G from this data, L and T, you data you have. So using this L and T data, you are finding G, and you see the length and time period of the pendulum are measured through 3 significance figures. That means your L would be given as, say, whatever, but up to 3 digits after decimal, not more than that. So if now I use this data and using a calculator, I get G is this, but this will not be a proper way to write, because your L and T you can measure up to 3 significant figures. So at most your G could be 3 significant figures. So G at most can be 9.821. But we have an extra addition. Your delta G is 0.02357. I'll tell you later also, we write the error always up to the first significant digit. Whatever digit comes, we write up to this, because if the error is 0.23, this is not much physical to write this 3, because error should be in approximation of one significant digit. So delta G could be approximately 0.0232. We don't write this 3 or etc. So the error is up to 2 significant digit. So your G cannot be, so using this, G can at most be 9.82. Is my presence is interfering with this? Still not. So G can at most be 9.82 as the error is 0.02. If error is 0.02, then G cannot be 0.001 level up with accuracy. We cannot report 821 or 822, 823. Everything comes within the range of delta G, which is 0.02. I'll give you another example later onwards. So that means G can at most be 9.82 with error of 0.02. That's why the answer will be this. So I think you got this. That directly comes from this concept first, then the errors, how to write the errors, how to write delta G. All the concepts will just go. But first of all, we cannot report this because of your L and T up to 3 significant digit. So just I restrict this up to this. Then this is not a good way to write the error. These are insignificant digits. Error is up to this. And that 0.02 deletes another digit from G, and it restricts up to 9.82. So things will be more simpler very quickly. Don't worry. Let's have a revision of how to represent the error. So the mass of an object is found to be 3.57 and with uncertainty of 0.033. If you write the mass as 3.57 plus minus 0.033, it will be wrong. This is absolutely wrong. The right answer is 3.57 plus minus 0.03. In error, whenever you're writing an error of something, delta of something, so always write a single digit. That error should always be of single digit. No, that's okay. So uncertainty should be reported with one significant figure. Suppose you find the length of an object to be 4.593 with uncertainty of 0.03. Will you write 4.593 plus minus 0.03? You will not. You'll write 4.59 plus minus 0.03. The result should be reported the exact order of precision of error and should never be reported more accurately than the error in measurement itself. Your reported data's accuracy should not be more than your error. Of course, if you, sorry, I got a call. Okay, so I'm back. So here, what I was trying to say is the uncertainty should, and the result should not be reported more accurately than the uncertainty itself. If the uncertainty has 2 digits of significance, that means up to 2 digits you are confident about the uncertainty, then you cannot be 3 digits of confidence, cannot have 3 digits of confidence in your reported data. Okay, so let's proceed. Next part is statistical analysis of small data set. Suppose we are giving a repeated measurement. Suppose you are measuring Jahir sir's weight, body weight. So we have a machine. Jahir sir is standing for here. This is a weight measurement machine. So if I stand up the weight measurement machine, I can have a different data and different measurements. No machine can be 100% accurate, and it will vary. You do a repeated measurement. In any case, in all cases, you can have slightly different values. So suppose the value obtained from a particular measurement is x, let's say it's right. The measurement is repeated n times. Sometimes n is small. We are dealing with small data set, say 5 to 10. How to calculate error from the small set of measurement? First, I get a mean of that. Of course, the mean. Sometimes I get 80 kgs, sometimes I get 80.5 kgs, sometimes I get 79.3 kgs, let's say. So you have a mean. Then we get a range. That what is the difference between the maximum and minimum? We are dealing with small data set, not large. In large, we have a different procedure, more accurate, more statistically valid procedure. So if you have a small range, so I find the range, then I find the uncertainty by writing r by 2 square root of n. N is the number of measurements. Then I write report measured values as x average plus minus square delta x average. That delta x average is r by range by 2 square root of n. Do you have an example? Yeah, we do have an example. Suppose I get 72 kg, 77, 83, 85, 88. I get 5 measurements like this in dataset 1. I better say this is machine 1. And it is machine 2. In another machine, you get 80, 81, 81, 81, and 82. So x average for machine 1 is 81. X average for machine 2 is also 81. You can just calculate average from here and there. So you have 2 machines. We get 2 sets of data. The range for data set 1 is 16. 88 is the highest data we got. 72 is the lowest data we got. So the range is 16. And here the range is 2, 80 and 82. So this data is more accurate, right? Definitely. This is more accuracy is there. This machine is not good. This machine is wrong. This machine is kaput. This machine is broken. This is not a good machine. So delta x. What was your delta x? Delta x is r by 2 square root of n. Delta x. So what is your n? 1, 2, 3, 4, 5. So your n is, we have 5 measurements. So here delta x is 8 by 2 root 5. Here your delta x is approximately, sorry, not 8, your r is 16, so it's 8 by root 5. So, and here it is 1 by 2 square root of 5. Sorry, not 1, it is 2. So approximately I get it 1 in a round figure, and approximately I get it in a round figure of, let's say, 8. No. I got it wrong. X average is this 2. I'm sorry. But actually I missed that step. Delta x is r by 2, and this is okay. I'm sorry. So I got, this is delta x average, and for delta x I think I should delete this altogether. That delta x average is r by 2, and for data set 1 I did this here, 16 by 2 root 5 delta x average, and here it is 2 by 2 root 5. Again, I'm sorry. This is delta x average. Sorry. Approximately I write it as 4. Approximately I write it as 0.4. So that machine gives you a very erroneous data, and that machine give you a good data. So that is how for a small data set we write the errors. So what about when the large data set is large? Then there is a different procedure in statistics. I call it the standard deviation. So of a large data set, the limit of an infinite number of measurements, not exactly infinite, a large number, the distribution of values follows a normal distribution. We have statistical analysis here, which I am skipping right now, that the values follows a normal distribution. The distribution has a peak at the mean value, x average, and the width given by standard deviation. Now let's see how this is calculated. So x average, you know what is average. You just add it up and divide it by number of measurements. You find delta x, this is sigma, as your standard deviation. How to calculate the standard deviation? You first calculate the average value, then for each and every value, measured value, subtract the average value, make a square, then add, divide by total number, then you do square root. That's what it's called, root mean squared. Root mean squared. You calculate average first, subtract the mean value, the average value from all experimentally measured values. You have x1, x2, x3. So then make a square, add, divide by n, square root. Just watch this term properly. Watch that formula properly. This is actually nothing but x1 minus x, the average, like this, divide by n, number of measurement, have square root over everything. Okay, then your average is what is delta x of average, which is actually a representation of error. So which is sigma by square root of n. Remember all those formulas and apply it accordingly. I will give you an example. Let's see. Suppose I'm measuring my weight and got data points in my machine like this. This is a relatively a larger data set. Okay. So then you add it up, do this exercise properly. First you do an average calculation, which will be, if you just do an average of all the data sets, so you get 84.359. Then your delta x, which is sigma, calculate the sigma. This is your homework. Subtract 82 minus 84.3529 square, make a square. Then add 82 minus 82.2 minus 84.3529 square. Then add all this after making a square. Divide by the how many numbers? 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15, 16, 17, I guess. Divided by it, 17. Then make a square root. That will be this. Thereafter, I think I should delete this. Should I have a, that is better. Okay, so then you calculate, first calculate this, then divide it by square root of n once again and get it 0.357. But we don't report it as 0.357. We report it up to one significant digit, the first digit, after an approximation. So we report this not as 0.357, rather as 0.04. And when it's 0.04, I not report as 84.3529, but rather I report as 84.4. Look here, I'm writing 84.4. This is 0.04, not 0.357, as we have learned it before. So do this homework. If you don't do, I am not certain if you're understanding. Calculate this yourself. You see that formula. Do it. So that is how do we calculate the error from a relatively larger data set. Okay guys, next will be a propagation of error. It is a very interesting thing, and as we know, we have a lot of discussion we can do, but we won't do that. We just know how to calculate it. Error analysis itself has a good books, a whole book were written about error analysis. So, but forget all about this. Just to have simple formulas. The theory of propagation of error tells me if my one variable z is x plus y, then the error in measuring z will be square root of delta x square plus delta y square. If z is xy, delta z will be mod of xy multiplied by delta x by x whole square plus delta y by y whole square. If z is x to the power m and y to the power n, delta z is square that mod xy square root of m delta x by x whole square plus n delta y by y whole square. That's important. And it is x by y. This and this remain same. This is just x by y. It is just xy. And if z is any other function, any function, this general formula applies here also. This is a generalization. These are special cases of what? Special cases of this is the general formula. This is the general formula. So okay, you just do this homework. If z is a function of xy, then delta z is this. I'm not proving this, I'm just telling you this. And if this to be true, get this from the mother form. I tell you the last line as mother form. So let's see, let's say this is mother form. So using the mother formula, you get everything. So at the first look, the formulas doesn't match what you usually know. Your previous knowledge may tell you that if z is x to the power n and y to the power n, then delta z will be, let's say, m delta x by x plus n delta y by y. This is z by z, so this would be x to the power n, y to the power n. This may not match you. You know this, right? But when you are doing this, things are not exactly same. If you do a delta z by z, so it is not exactly same. Did I get any mistakes there? Just let me check once again. I did a mistake, so sorry about it. To the power n, y to the power n there, otherwise everything would be problem. Okay, so we have it, no issues. Okay, so what I was telling you, that this is highest possible error. This is also not wrong. This is usually done in class 12 level of book. And these are expected error. Used more frequently by physicists. This is expected error. That if you have a quantity this, your error, most expected error will be in this range. As the errors itself follow the normal distribution, using that property, we got these formulas. This is an algebraic mother formula. And if you got delta z by z, you get this. So better to write as delta z by z. That things cancels. Right? That is great. That doesn't work much. May I change the color? No, I shouldn't. So everything is, you can change it by z by z. I think that is more familiar formula. This. Sorry. That takes mod of so. Okay. That's great. That's great. So okay guys, we use this as we are undergraduate students, so we use this. So now we give you example. A resistance is measured by passing a current through it and measuring the resulting voltage drop. That means we are measuring a resistance. Resistance is R. Resistance is measured by passing a current. We pass a current and measure the resulting voltage drop. Okay, so I think if we just divide this into sides. No, just delete it. Okay. And measuring by resulting voltage drop. If the voltmeter and ammeter have resistance uncertainties 3% and 4%, so what I am trying to do is V equals to IR, R is V by I. I want to measure R. Voltmeter and ammeter have resistance 0.3%. That means this 3% means it's 0.03, and this delta I by I from ammeter. Okay, then what is the uncertainty in resistance? Delta R by R. Uncertainties. 3% uncertainty of some quantity, that means delta V by V is 0.03. 4% uncertainty of something in ammeter, that means in current, it is delta I by I. So if I have this, now you think about the question. You have a voltmeter, you have an ammeter. We are trying to find the resistance. So you know the value of I and R with their uncertainties. You need to find the uncertainty in R. What I do. Okay, guys. V equals to I by R. Is V by I. Better to write in this form. Okay. So from our general formula, if R is V by I, then your delta R would be delta r by delta v square, delta r by delta I square. So it's simple. If you have divided by 2, or m is 1, n is minus 1, just simply delta x by x, delta y by y. So it is nothing but delta r by r is delta v by v whole square plus delta I by I whole square. Just think about those formulas, man. Think about it. Don't just use it. Don't just use what I am trying to say. Just use delta r by r. Don't do it. Don't do. This is the usual class 12 notation, but this is highest error, highest possible error. But as a physicist, we actually don't do this. Uncertainty in the value of resistance, we use that general formula. And using that general formula, we get delta r by r is this. So delta v by v is 0.03, delta I by I is 0.04. So that delta r by r will be 0.03 whole square plus 0.04 whole square is 0.05. That expected uncertainty is 5%, not here if we just add it, not 7%. That 7% answer is the highest possible error, and the expected error should be 5%. We just don't add, we do a square of both, add, then do a square root. All comes from this, or if you think comes from this. So do all this from the mother formula. Okay, friends. If we try to, if you ask what will be the uncertainty in power in the previous examples, you got everything. Delta v by v, delta I by I, delta r by r. What is with the uncertainty of power? For power, small p, that's it, origin, capital P. P is v by vi, so delta p by p will be delta v by v whole square plus delta I by I whole square. It has a 5% uncertainty. But one lesson has to be learned from here also, that you might have written, you might have written p as I square rt and calculated the error, but that will again be wrong. We should change the color from red to green. That green is traditionally signifies the right things. So okay, and in red we mostly cut, so then your answer script with red. So okay, so if we have one quantity and you can write its two type of expression, like one is vi, another is I square rt, and calculate the error, but that will be wrong. Why? It will give you increased error. But error should always be calculated from the most basic observations. We observed v and I, and we got that uncertainty. If I can write power in terms of the very basic quantities, which is v and I will write it and calculate error from there. Your r is a derived quantity, which we have derived from v and I. Then I write r. So if you write p like this and calculate the error will increase. The lesson is always write the quantity by as less with as less time number of quantities you can, and most basic quantities you can. R is derived. R is a derived quantity from V and I. So I don't use P this formula when calculating the error. Rather, I use P this formula. V and I are most basic. Okay. So now let's give you a different example. Is my presence effect impact this? I don't think so. This is another example. Let's sometimes in error analysis you can give a data points which may be a graph fit. Okay, let's see. Both the data points and a linear fit of the current versus voltage. This is V, this is I, in a graph. As you have done in lab, that we try to find a straight line which fits all the data points. So we do this. So your data points are given here and a fit. If the error in the slope is 1.25, what is the slope? You might have already forgot. What is the slope? Slope is y by x. That slope is y equals to mx. No c is there, no constant. The equation of a straight line is y is mx plus c. As the straight line passes through the origin, the y is mx. The slope is m. And that means your I is mv, slope multiplied by the voltage. I is v by r also. So what does your slope represent? Slope represents 1 by r. V is IR. I is v by r. So your slope from this graph represents the inverse of the resistance, the reciprocal of the resistance. In your data, we have I versus V. The slope of the graph will give that proportionality constant, which is multiplied in I and V relation, and which has to be 1 by R from Ohm's law. So your slope in this graph is 1 by 25. So resistance from this graph is 25. Just give me this data. I'm telling, okay, my friend, your resistance is 25. As simple as that. 25 volts, 1 ampere. So resistance is 25. V is IR. Now, very simple. Delta R by R is delta M by M. R is 1 by M is 1 by R, or R is 1 by M, one direct variable. Just these are called logarithmic derivatives. Don't worry about it. Just have a common formula there. So no y is there. So delta z by z is this. So if only one single variable is there, so say and z is x to the power m. So delta z by z is m delta x by x. As simple as that. So this is this. So delta r is r into delta m by m. R you have already got. Delta m by m given. So delta m is given actually. And m is calculated. That delta m is 1.255 into 10 to the power minus 3. Using this, I get it this. Use the value m as 1 by 25. So then I get it as 0.8. That's very simple and straightforward. I don't think there should be any other issues there. another problem. These are the problem asked in previous years CSI and NET. Two physical quantities T and M are related by the equation. T is this. A and B are constant parameters. Variation of T as a function of M was recorded in an experiment due to determine the value of A graphically. Let M be the slope of the straight line. I should what happened? Oh, that's great. Here I delete the answers so that you can focus on what I am actually. Okay, so T and M are related by the equation like this. So if you get a square, so you get T square is 2 pi by A whole square M plus 2 pi by A whole square B by 2. Sorry. Okay, got it. So the T square versus M should be a straight line. The variation of T as a function of M was recorded in an experiment to determine the value of A graphical. So you used this. Okay, let M be the slope of the straight line. Small m should be the slope of the straight line. When T square is plotted versus M, the slope will be 2 pi by A whole square divided by 2. The uncertainty in determining A, it's a very, very simple problem. When I plot T square as a function of M, I am plotting this relation. T square is 2 pi by A whole square, capital M by 2 plus 2 pi by A whole square, small b by 2. Then what is asked? M is the slope of the graph. I write it again. So what is the slope? Slope is this. So T square is small m to m plus c. So small m is 2 pi by A square half. That's it. So the question is, if delta m is the uncertainty in determining m, what is the uncertainty in determining A? So my question is, what is delta A? Should be very simple, just one variable problem. Your T square is this, this is this, this is this in a typed format. Whatever I have written it here, I wrote it there. So m is half of 2 pi by A whole square. So your C is 2 pi by A whole square B by 2. That is not relevant here. So from here, m is this, 4 pi square by A square half. So it's 2 pi square by A square. So delta m by m is 2 delta A by A. That's m is proportional to A square, or A to the power minus 2. that minus doesn't matter. Error are in absolute values only. So your delta A is A by 2 delta M by M. Very, very simple. No issues. No way. There are no other ways to get mistakes. All are very simple. Okay. Now if you do 2 exercises, pause the video there. Make a great pause. Make a pause and answer. Make a good pause. Make a pause. Make a pause. Okay. So anyways, so if you answer these 2 questions correctly, then you are done. Answer is C, answer is B. Pause. This is C, this is B. Get it done, my boys. My boys and girls, of course. Okay, now last. Error in counts. There's an sometimes you are asked. Suppose a detector is used to count the number of gamma rays. Delete. First by question. The question on that it should be. That's how the ideal teaching should be in the slides. Okay. So suppose a detector is used to count the number of gamma rays emitted by radioactive source. We have a detector and we are counting the number of gamma rays emitted by a radioactive source. You have a radioactive source and you have the detector. If the number of counts recorded in exactly 20 seconds is 10,000. So 10,000 times the detector given signal in 20 seconds. And very fast. Very fast, isn't it? You cannot, if we as a human, we cannot count this. In 20 seconds, we get 10,000 signal. Tick tock, tick tock, tick tock, tick tock. In 1 second, I can at most count 3, 4, or 5. Okay, but I cannot count 20 seconds. 10,000 times of tick tock, tick tock, tick tock, tick tock. Okay. So, okay, so 10,000 times the signal given in 20 seconds. The error in the counting rate. What is counting rate? So then counting rate is, of course, 10,000 by 20. So it's 1,000 by 2. It's 500. So what is the error in this rate? Counting rate is okay, 500, but it may vary. It may, of course, vary. That's why we're calculating an average. 20 seconds, we got 10,000. So on an average, we get 500. But that on an average, that means it has some error. So it has some error. Error in the counting rate. The counting rate. Your n is 500. What is delta n? The answer is, okay, it should be there. First slide should be this. Second slide should be this. Okay. Whenever some count or rate per second type of things come, the error will be rate per second. Square root of. So here rate per second is this. I should n equals to, that is your counting rate, is 500. This is your n. The error will be rate per second, that is square root of n. Your n is 500, so the error is square root of 500. Should be green. So this error is square root of your count, 500 square root, you get 22.4, approximately 22. So I write n is 500, delta n approx 22. So the counting rate approx 500, 22. We get radioactive source detector, tick tock, tick tock, tick tock, tick tock, 10,000 times. We report it in 20 seconds. So on an average per second, we get 500 counts. But with how much error is it? How much expected error? That is square root of 500. Square root of 500. Remember it. So okay, these are all I could teach you in error analysis. In the next class, we'll be learning velocity and acceleration in plane coordinates. You can contact me anytime there. You can have a subscription of the course here in this link. You can contact me. And lastly, thank you.